Hi everyone, welcome to part 7 of lecture 11, and in this lecture we will discover the covariance and the correlation coefficients. So these two terms are really important and probably you will use them in some other classes like statistics and some other lectures. So please try to understand it and try to understand the basic logic behind that two terms. So let's start with the covariance, and the covariance can be defined as a quantitative measure of the strength and the direction of the relationship between two random variables. So let me make it more clear. Let's say we have two random variables and we want to know that when we change the one of them, how the other one will change. Okay, so to analyze the level of the change or the direction of the change, we use the covariance. So the covariance of two random variables x and y, which is denoted by co x and y, and we can calculate the covariance of that two random variables as the expected value of x minus expected value of x times y minus expected value of y. So it is easy to calculate that one. And when the covariance of two random variables is 0, we say that the x and y are uncorrelated. The changing one of them will not affect the other one. Okay, there is no correlation between the x and y if the covariance of that two random variables is 0. So it is sign. Actually, the value of the covariance is not not so important, but the sign of the covariance is important. Okay, because the sign shows the whether x minus expected value of x and the y minus expected value of y tend to have the same or the opposite sign. I mean, if they are in the same sign, that's mean changing one of them, like the increasing one of them, will lead to increase the another one. Okay. So that's mean if the y values change high or bigger, the another one also will change in a bigger manner. Okay, but in the opposite sign, changing one of them will cause the decreasing in another one. Okay, so the important one is the sign of the covariance. The covariance doesn't show you how they are related. Okay, that is the important point, and that's why please focus on the sign of the covariance. The sign of the covariance will show you the direction of the change, okay, between two variables. Or in other words, we can say that the covariance shows how two variables behave together, okay? And an alternative formulation is the covariance of x and y, which is equal to expected value of xy, x times y, minus the expected value of x times expected value of y. So if you do the multiplication here, you will get that one, okay? And that is the easy to remember, so you can use that formulation to calculate the covariance of two random variables. So we have some properties. By the way, if you didn't understand why I try to get your attention about the sign of the covariance instead of values, we will solve the some examples and I will explain in details to make it more clear. Okay, but just to remind you again, the sign of the covariance is much more important than the value of the covariance. So let's look at some properties. If x and y are random variables, we have the covariance of x and y, which is equal to covariance of y and x. Okay, and the covariance of x and x, so the covariance of a random variables with itself, which is equal to the variance of x. Another one is the covariance of x with some linear combination of some other random variable, which is equal to the a times covariance of x and y. Okay, so these constant values will not affect the covariance, but the coefficients will affect. So that will be the coefficient of the x and covariance of x and y. Also, the covariance of x and y plus z, the sum of two random variables, which is equal to the covariance of x and y plus covariance of x and z. So if you remember these properties, the things will be much more easier for you. But if you don't, you can just look at some source. So if x and y are independent, the covariance of x and y is 0. That is for sure. Okay, that is for sure. But the converse is not necessarily true. So if the covariance of x and y is 0, we cannot claim that they are independent. Okay, that is important, and we will see that properties. For example, let's say we have a random variable which is uniformly distributed between -1 and 1, and we define a new random variable y, which is x squared. Okay, so here the x and y are clearly independent, strictly independent, because if you know the value of x, you will immediately know the value of y. They are perfectly independent, perfectly dependent. Okay, so let's calculate the covariance of x and y. The formulation is the expected value of x times y minus the expected value of x times expected value of y. All right. So x times y, which is simply equal to x cubed, and y is x squared. So it is simply, we can rewrite this part as expected value of x cubed minus the expected value of x times expected value of x squared. Okay, let's calculate the third moment of the random variable x, which is the integration of x cubed times 1 over 2, right? The expected value of x cubed, y, which is y1 1 over 2. Let's say that is the uniformly distributed. So between -1 and 1. So the area here is 1, the total area, and the length is 2. So the height, the probability should be 1 over 2, right? 1 over 2 times 2, which is equal to 1. That's why the corresponding probability is 1 over 2. So we need to integrate that guy, the x cube, over the domain between -1 to 1. And we can do the same thing for here, which is x times 1 over 2. That will be integrated over the domain x -1 to 1 times the same thing for the x squared. If you do the simple calculations, you will get the 0. So the covariance of x and y, 0. But they are dependent, strictly dependent. So if we know the covariance of two random variables is 0, we cannot claim that they are independent. As you've seen in this example, even though they are strictly dependent, the covariance is 0. In other words, the covariance is a measure of the linear dependence. That's mean, can you describe a random variable as a linear combination of another random variable? Like if you can describe the x such that ay plus b, you can linearly, the x is linearly dependent on y, the covariance will not be 0, okay, because they are linearly dependent. You can define x as a linear combination of the y, okay, or linearly, you can define the x as a linear function of the y, okay. So the covariance is a measure of the linear dependency. Here, the dependency, the x and y are dependent, but they are not linearly dependent, okay, because y is equal to x squared. They are quadratically dependent, okay. You cannot define the y as a linear function of the x. That's why we got the 0, okay. So the 0 meaning the no evidence of the linear dependency, okay. We don't have any evidence for that one. But that doesn't mean that they are not dependent. As I said, they can be dependent in other form, as in this one, that they are quadratically dependent. Okay, so that's why, to summarize that one, if you know the covariance of two random variables as 0, you cannot claim that they are independent. Okay, they can be dependent, as we see here. Also, the covariance shows the linear dependency, the measure of the linear dependency. And the last one is, as I said at the beginning, the sign of the covariance is important. We can summarize this three, or we can focus on these 3 points so far. Okay, so another one is, okay, so we know that, let's say these two random variables are dependent, but what is the level of that dependency? What is the strength of that dependency? Okay, to measure that one, we use the correlation coefficients of two random variables, x and y, that have non-zero variances. Is defined as the covariance of x and y, and we will scale that covariance of that two random variables with the square root of the variance of x times variance of y, the product of the variance of that two random variables. So here the important one is the correlation, the covariance doesn't measure the strength of the dependency, but the correlation coefficients measure the strength of the dependency. Okay, how strength their dependency situation. Okay, so the results of the correlation coefficients is always between -1 and 1, and also if the correlation coefficient is 1, the absolute value of the correlation coefficient 1, if and only if y minus expected value of y is equal to c times some constant value times x minus expected value of x. Why? Because again, we want to measure the linear dependency. If you can define the y minus expected value of y as a linear function of the x, for sure, you will get the correlation coefficient 1. So that's mean if you have a -1 or 1 as a result of the correlation coefficient, you can say that I can clearly define one random variable with another random variable in the form of linear. Okay, so that's why the correlation coefficient is a measure of the strength of the linear dependency between the x and y. So let me give you an example to make the things more concrete. And suppose that we are given the probability mass function of the x and y as shown in the table, and let's calculate the correlation coefficient of the x and y. Okay, so the first thing, we need to calculate the covariance, right? And to calculate the covariance of two random variables, we need to use these formulations, right? To do that, first we need to calculate the expected value of x times y, and also we need to calculate the expected value of x and expected value of y. So let's do that. The expected value of x is easy, right? So x can take 1, 2, 3, and 4, and we can calculate the expected value as 1 times 3/20, 2 times 5/20, 6/20, and 2 times 8/20, plus 4 times 3/20, right? So that will give me the expected value of x, which is simply, remember that x, summation of x times probability of x, which is the expected value. Okay. So the expected value of x is 51/20. And how can I calculate the variance of x? So just remember that, which is the expected value of x squared, the second moment, minus the expected value of x squared, right? So I know the x values and corresponding probabilities. So for example, for the first one, 3/20 times the x squared. The first value for the x is 1 square, plus 6/20 times 2 square, etc. This part is the expected value of x squared, okay, minus this one is expected value of x. I have just calculated here, and I will get the square of them. So the result is this one. So 339/400. Okay, so I know the expected value of x and the variance of x. Now let's calculate the expected value of y and the variance of y. So again, from the table, to calculate the expected value of y, the first value y will take is 1, and the corresponding probability of sum of these 4. And the second one, y can take 2, and the corresponding value is summation of these guys. Okay, so the logic is same. And the expected value of y will be 5/2 if you do the same calculation. And the variance of y, again, we will make the calculation based on the expected value of x squared minus the expected value of x squared. And then I will get the 17/20. Okay, so now I know the expected value of x, the variance of x, and I know the expected value of y and the variance of y. And the last thing, I need to calculate the expected value of xy, right? X times y. So in this case, I will use the table like expected value of xy is 1, 1, right? And I know the probability of the corresponding probability I know, which is 1/20, right? So I will simply multiply the corresponding probability and the corresponding values, and I will get 33/5 at the end. So now I have all the things, just I need to use them to calculate the covariance, okay? So the covariance is the expected value of xy, x times y, minus the expected value of x times expected value of y. So I know just the results of the value of these expectations. I will just put that numbers into the place and the formulations, and I will get the 9/40. Okay, so that is the covariance. But that 9/40 will not give me the strength of the dependency. But I just know that there is there's a positive relations. That mean when I increase some random variables, the other one also increase. Okay, but I don't know the strength of them. So the direction is same. Let's say that is the base level. If the x goes up, the y will go up. Okay, so that is, or if x is go down, the y will go down. So I know that kind of dependency, the dependency in the same direction. But to measure the strength of that dependency, I need to calculate the correlation coefficient, which is simply the covariance of x and y divided by square root of variance of x times variance of y. So I just know all the possible, all values, and I just put in the formulations. I will get the approximately 0.26, okay? So that is shows the strength of the dependence. So let's say that is x and that's y, and if the correlation coefficient is 1, that is y is x. There is a perfect positive relationship, dependence here, okay? If this is something like that, the correlation between x and y, maybe that is something like that, okay? So if the correlation coefficient is -1, the directions will be something like that, okay? So that's why there is a positive and respectively powerful dependency between x and y, and we know that that dependency in the same direction. Okay, for the continuous case, we will do the same thing, and suppose that we are given the joint PDF of x and y as follows, and we will calculate the correlation coefficient of x and y. So to do that, the logic is the same. We need to calculate the expected value of x, expected value of y, the variance of x and variance of y, and expected value of x times y. But to do that, we need to figure out the marginal PDF of x and marginal PDF of y, right? Because just remember from the previous part, we can just fix the one random variable. Let's say if you want to reveal the marginal PDF of x, I need to fix the x and I need to integrate the joint PDF for all possible y values, okay? We did that before. You can just revisit the slides. You will end up with this guy, the marginal PDF of x, which is 4x minus 3x squared, okay? And that is valid for all x between 0 and 1. So to calculate the expected value of x, we need to integrate x times the marginal PDF of x over the domain between 0 and 1. And if you do the same integration, you will get the 7 over 12. Okay, so these are the simple things, so that I will just skip them. And also to calculate the variance of x, you can first calculate the second moment, the expected value of x squared, which is again, I just need to integrate the x squared times 4x minus 3x squared, which is the marginal PDF of the x, and which is the x squared, the second moment of the x. And if you integrate that one, and also the x, we have already calculated the expected value of x here to calculate the variance. We just need the square of the expected value of x. You will end up with this value, 43 over 720. Okay, so that is the variance of x. And now we need to calculate the expected value of y and the variance of y. To do that, we need to reveal the marginal PDF of y. And in this case, we will fix the y and we will integrate the joint PDF for all possible x values. We did this before and we get the 4y minus 3y squared, okay? If you don't remember how we get this one, please just revisit the previous slides. So that is valid for the all possible y values. So the expected value of y is same. That is the integration of y times 4y minus 3y squared dy. If you do that simple integration, you will get the 7 over 12. And for the variance, again, we can use this formulation. First, calculate the second moment, and then expected value of x squared. We have already know the expected value of y. And we just need to calculate the expected, the second moment, so which is the y squared times the corresponding marginal PDF. If you do that simple integration, and again, you will get 43 over 720, okay? So that is the same. Variance of x and variance of y is same. And also the expected value is same. And the last thing is we just need to calculate the expected value of x times y. So again, that is the joint, we can use the joint PDF, which is simply the double integration of x times y times the joint PDF with respect to dx and dy. If you do that, if you make that multiplications and do the integrations, you will get the 1 over 3. Okay, so we know that one. Okay, you can simply do these things. So now we know all the things we need to calculate the covariance and the correlation coefficients, right? Let's first calculate the covariance of x and y, which is the expected value of x times y, minus the expected value of x times expected value of y. So which is 1 over 3 minus 7 over 12 times 7 over 12. And we will get the minus 1 over 144, okay? Now, that is a negative sign, right? So that's mean these two guys, that two random variables, have a dependency in an opposite direction, okay? So we can conclude that results from that sentence from these results, okay? And the last thing is the correlation coefficients, which is the covariance of x and y divided by the variance of x times variance of y, the square root of variance of x times variance of y. If you do the calculations, you will get the minus 0.12, the approximate. So that shows the strength of the dependency, the linear dependency. And also we know that that is in the opposite direction, as we've seen in the results of the covariance. But we cannot say that is too powerful, but again, it's a more than zero. So there is a dependency, the linear dependency, in an opposite direction with that strength, okay? So that is how we can interpret the covariance and the correlation coefficients. So that is the end of lecture 12, and also that is end of this class. So thanks for watching. I hope you will make all these things more concrete and you will use in the different classes, different lectures. I hope I will see you in some other lectures.